Hi everyone, I'm Jeremiah and I'm going to talk to you about breadth first search. When we talk about searches, one group of searches we can look at is what's called a brute force search. And brute force search is a technique where we try to look at all the possible problem states, and in the case of a graph that means all the vertices in a graph, in order to find the solution. Here, that's a path. By its nature, there are a few things that are true of a brute force search. Brute force searches are systematic, that is, they proceed in a specifically ordered fashion. And they are also exhaustive, meaning that if we have a finite space, it will try all of the possible options. For example, let's say we're trying to plan a path through this graph. Our initial point is I, and our destination is D. A brute force search might proceed like this. We start at I, and we start building out a tree along the nodes that we visit. So A is a child of I, as well as B. If we go to A, we have a few options. We could go back to I, we could go to B, or we could go to D. If we're at B, we could go to I, A, or C, and so on down the line. Now there are some challenges we run into with brute force searches, in particular related to what we call the branching factor. When we talk about the branching factor, we're talking about how many connections or how quickly the problem set grows. In the case of a graph, that is usually defined by the number of connections on average that a vertex has. So let's consider a large graph that has a branching factor on average of 2. Each ply, that is, each level in our tree, represents a connection on the path. It represents a step from one vertex to another. So if we have a tree that's 2 ply, that is, it has 2 levels, then the number of nodes in that will be 2 squared minus 1, which is 3. And if you think about it, that makes sense. We have the root node, and then we have its 2 children. If we go 16 levels down, that's about 65,000 nodes. So far, so good. But we did say this was a large graph. What about 50 or 100 levels? If we go down 50 levels, what we'll see is that the number of nodes is growing really quickly. We now have over 1 quadrillion nodes. And if we went down 100 levels, that gives us 1.27 times 10 to the 30. And it may not immediately be obvious, but this number is really, really big. This is 1.27 nontillion. And to give you an idea of the scale, at that level, even with this very simple graph, and if you had a highly optimized machine with 16 cores, each running at 4 gigahertz, and with pipelining, if it only took 2 cycles for a single instruction and 10 instructions to process a node, and even if this machine had perfect parallelization, in other words, even if it was acting as if it were a single 64 gigahertz processor, it would still take longer than 10 trillion years to go through all these possibilities. So we're not talking about a minor optimization here, we're talking about a very serious growth problem. So why is this happening? And the answer is we're running into a lot of duplication. We're duplicating the visitation of problem states. And you may have already picked up on this in the first couple of slides. Unless we explicitly build it into our algorithm, a computer may go over and over again through the same problem states, through the same vertices in our graph. So eliminating duplicates is going to save us time because we're only going to explore each space once, and it's going to make it possible for us to address problems that otherwise would be practically unsolvable. However, it does come at a cost. What that means is that we have to remember every place that we've been, and we're going to have to use memory and time to do that. So here's our example from the beginning one more time. You can see that even just 2 levels down, we're already running into lots and lots of duplicates. And in search problems, this is really common. The further down we go into the search, the higher percentage of everything we see will be a duplicate. So it really makes a big difference when we eliminate these duplicates by doing a check. So the first specific search technique we're going to look at is called a breadth first search, which is a brute force approach that explores all of its neighbors before it explores any of the neighbors' children. The main difference between a breadth first traversal and a breadth first search is that in a breadth first search we have a goal check. That means that after we pull an item off of the queue, the first thing we're going to do is check it to see if it is the goal. And if it is the goal, we're going to terminate the search because we found what we were looking for. In contrast, in a breadth first traversal, we have no goal check, so we keep going until we've explored all of the space, no matter what. Breadth first search has a couple of features that are special to it. It is what we call an uninformed search. That means it has no special knowledge of the goal that helps it guide the search. And there are many alternatives that are informed searches. If you're interested, you might want to look into this when you get to an AI class. Breadth-first search is also an optimal search in terms of the number of steps. That is, it will always give you the solution that requires the fewest number of steps. It's important to distinguish between the number of steps and the cost, though, because some steps might be more costly to take than others. Breadth-first search is also a complete algorithm, which means that it guarantees to find a solution if it exists. It's also exhaustive, meaning that if we have a finite state space, it will eventually exhaust all the possibilities. And it's systematic, meaning that it proceeds in an ordered fashion. But let's take a look at an example. Let's say we have another graph, and again we're going to go from I, the initial point, to D, our destination. We're also going to establish a queue that we can use to iterate on in breadth-first fashion. So, the first thing we do is we put our starting point in the queue. That's I. Once we've done that, while the queue is not empty, we will proceed. We pull the first element off of the queue. In this case, that's I. And the first thing we do is the goal check. Is I the goal? In this case, it's not. And then we see what children, that is, what connections I has. I is connected to A and to C. We're also going to keep track of how we got to these vertices, A and C, using a pointer. In our example, we'll use an arrow to represent that pointer. Now we're finished with I, and we restart the queue's loop. The queue is still not empty, so we pull the next element off, which is A. A is also not the goal, so we look at its children, its connected vertices. In the case of A, it's connected to I and B. However, we've already been to I, so we're not going to add it to the queue. And this is where the duplicate check comes in. Every time we consider a child, in this case a connected vertex, we have to ask, have we been here before? In the case of breadth-first search, if we have been there before, then we do not add it to the queue. We do nothing with it. However, B is not a duplicate, so we will add B to the queue. And then we're done with A, and the loop starts again. The queue is still not empty, so we pull C off of the queue. C is not the goal, so we look at all of its children, which are I and E. I is a duplicate, but E is not, so E will go on the queue. After we're done with C, the next element on the queue is B. B is also not the goal. It is connected to A, D, and F. We've been to A, but we have not been to D or F, so we'll add D and F to the queue. Being done with B, we loop again, and this time we pull E off of the queue. E is also not the goal. E has two children, C and F, but both of them are duplicates, and neither of them will be added to the queue. So we're done with E. This time, when we start the next iteration of the loop, we pull D off of the queue. D is the goal, so we stop here. The search is done. Now we trace back. We got to D from B, B from A from I. So our path is I, A, B, D. So that's breadth-first search from a conceptual point of view. But how would we actually put it together in code? Well, let's take a look at an example. This example is written in Python-style pseudocode. We'll assume that we have the starting and goal points coming into the algorithm so that we know where we're starting and where we want to go. First, we need to create a queue. We're going to use a list for this, and we're going to call it open. We often colloquially call this the open list. And we're also going to have a visited map that will help us keep track of where we've been up to this point. As you saw before, the search branches out in a tree-like fashion, so we're going to need a tree node in order to store this data. We're going to call that a planner node. The planner node in this case has two parts. It has a vertex, the location we're trying to represent, and it also keeps track of a parent. From the starting point, there is no parent, so we'll set that to null or none in Python-style code. We'll create this new map, visited, and by default, we'll have only the starting point in it. The key for our map will be the vertex itself, and the value will be the planner node that represents that location. This will make it easy for us to find the planner node if we have the vertex. We'll also add that to our open list. And then, while the queue is not empty, while the length of the open list is not 0, we'll pull the first element off and we'll store that in current. If current's vertex is our goal, then we're done. We'll build and return the solution. Otherwise, for each of the edges within current's vertex, we'll find the vertex at the end of that edge. And if we have not visited that successor, that is, if that successor is not in the visited map, Then we'll create a new tree node, a new planner node, wrapped around that successor that keeps track of its parent, which is current. We'll add it to the visited map so that we know we've been there, and we'll also add it to the queue. And we'll continue this cycle until we find the solution or until we run out of possibilities. While breadth-first search can be an effective solution, it does have some problems. One of them is that it uses a lot of memory and a lot of time. That is a pretty common problem in search algorithms. There's never quite enough power or enough storage. The other big problem is that it is optimal only in terms of steps, not necessarily in terms of cost. In our example here, it's clear that the path ICD is longer than the path IABD. However, because our algorithm only cares about the number of steps and not the cost, it would select the longer path over the shorter one. There are many ways we can build from breadth-first search to make better and stronger algorithms, and we'll do that now by taking a look at a class of algorithms known as best-first searches and one particular example of a best-first search. Best-first searches consider the vertices or the problem states according to which ones appear to be best for some specific measurement, and they sort the queue based on that information. In practice, this is usually done via a priority queue, as this allows us to bubble the best element to the top without too much extra work. One specific example of a best-first search is what we call uniform cost search. Uniform cost search is a variant of Dijkstra's algorithm, and it sorts its list according to the cost up to this point along the current path, what we call the given cost. When we say the given cost, we mean a cost that is known. Just like in mathematical proofs we say something is given, here we say given because we know the cost. Uniform cost search has a lot in common with breadth-first search, but it does diverge in some interesting and important ways. It's still an uninformed search because it's not using anything to guide that search. However, uniform cost search is optimal in terms of cost for any valid cost definition. That cost could be steps, it could be distance, it could be weighted distance, it could be any valid cost mechanism. This in particular makes uniform cost search a very effective alternative to breadth-first search. It is by its nature also complete, exhaustive, and systematic. So let's take a look at an example. If you take a look at this graph, very quickly you'll see that breadth-first search would choose the path with the fewest number of steps, ICD, which would cost more than the shortest path in terms of distance, IABD. So let's see how keeping track of the cost up to this point impacts the results. Again, we're starting at I and going to D, so we put I on the queue, and then while the queue is not empty, we pull the first element off. In this case, that's I. I is not the goal, so we look at its children. It connects to A and to C. A's accumulated cost from the starting point is 1, and C's is 5. So the order of the queue will be A, C. When we're done with I, we restart the loop. The queue is not empty, so we pull A off of the queue. A is also not the goal, so we look at its children. I is a duplicate, but B is not. B's accumulated cost along the current path from the starting point is 7. That's more than 5, which was C, so we put B after C. Now, even though I is a duplicate, it's no longer enough under uniform cost search to immediately throw it out, because it's possible that there might be two different paths to a vertex. So we have to compute both costs and see which one is better, and keep the better of the two. That will often be the first one, but not always. In this case, it's trivial to see that it would cost more. If we went from I to A and back to I, that would cost us 2, and 2 is more than 0. When we're done with A, we restart the loop and pull C off of the queue. C is not the goal. Its children are I and D. I is a duplicate, but D is not. D's accumulated cost from the starting point is 10, which is more than 7, so we put D after B. Again, we can't just cast out I, but we also know that I's given cost is 0 because it's the starting point, so we're not going to put it in the queue again. When we're done with C, we restart the loop and pull B off of the queue. Now things start to get a little bit interesting. B has 2 children, A and D. Both of them are duplicates. Let's start by looking at A. You can probably already see that the path going back to A is going to cost us more than the original path. The original path, I to A, was 1. The new path, IABA, would cost 13, so we're not going to do anything with A. However, when we look at D, it's a different story. The original path, ICD, was 10. but the new path, IABD, is 8. That's less. As a result, we need to change the cost and the parent of D. Changing the cost is just a matter of updating the number, and changing the parent is a matter of changing the pointer to point to B instead. Once we've done that, we're done with B. So we restart the loop, pull D off of the queue, and D is the goal, so we've reached our destination. We can now trace back and get our path, and it turns out that it's IABD. So let's take a look at some more pseudocode. Let's start by looking at our planner node class. The biggest difference here is that now we have a given cost which we need to calculate and store within the planner node. If we look at our algorithm, we're going to start from a breadth-first search because this is based on a breadth-first search. But we're going to make some modifications so that we can use a priority queue. You can see the changes highlighted in yellow. The first step is to change the data structure itself and to pass in a comparison function. And we'll get to that pretty shortly, but keep that in mind. We also need to change how we construct the planner node to make sure we're adding a given cost. And instead of using a standard list append function, we're going to use a priority queue's push function. When we pop a node out of the queue, we're going to pop the best one, which in a priority queue is going to be at the top. The calculation of the new cost is based on two things. What is the cost to get to the parent, and what is the cost to get from the parent to this new location? We take the cost to get to the parent, that is, current's given cost, and we add the cost of this edge, the path that we're going to travel along from the current to the new node, and together they give us the new given cost of this particular location. If we've never been here, just as in a regular breadth-first search, we go ahead and add the new node. However, if we have been to this location, it's not enough to just throw out this location, because we might have a better path. We have to ask, is the new cost better, that is, less than, the old cost? If the new cost is better, we'll change the given cost, we'll change the parent, and then, so that any children are also reprocessed, we'll put this node back into the queue. Finally, the comparison function is very simple. We take a left-hand side and a right-hand side planner node, and we return if the left-hand side's given cost is greater than the right-hand side's given cost.